We're going to begin with integrating factors. So integrating factors, I'm going to integrating factors are functions of x and y that, when multiplied against our differential equation, make the differential equation exact. So let's presume we have a differential equation of the form that we've seen for both separable and for exact equations. But let's say we aren't able to separate them, nor are we able to meet the condition for exact equations. And this is the condition that makes it exact. So let's say that can't be done, and our equation is not exact. Well, an integrating factor is a function, x and y, that's multiplied against our terms in our differential equation, that make the equation exact. So if we take the differential of mu m, it will equal, I got that wrong. Okay, dy of mu m is equal to d dx, partial differential of mu and n. If this holds, and that function makes the equation exact, then we can use the methodology to solve for an exact equation. So what we have is m d mu dy plus mu dm dx is equal to n d mu dx plus mu dn dx. And if we can find that mu of x, y, that makes this so, then we can solve the difference. There's a solution. And what we have been told in the book is of a special case of important sets of cases, actually, where mu is actually a function of one variable, either of x or of y. So if it was of a single variable, then we have, in our first case up here, if it's, let's say, mu is equal to a function of x, then that term up here is 0, because du dy would be 0. So we have mu of dm dy is equal to n du dx plus u dn dx. So what we have is u dm dy is equal to n du dx plus mu dn dx. Now, if mu is a function of x, g of x, then the partial derivative of mu is actually is d dx. So now we can solve. We have, if we just start bringing things over, we have n du dx is equal to mu of dm dy minus dn dx. And now a couple more dm dy dn dx divided by n, and then we have du on u is equal to dm dy minus dn dx on n dx. If you take notice, what we're doing is remember our linear differential equation where we had y prime plus p of x y equals g of x, and we had mu equals e to the p of x dx. That's similar to what we're doing here. So we have the natural log of mu is equal to dm dy minus dn dx divided by n dx. And then mu of x is equal to e to the integral, see the similarity, dy divided by n dx. So we can solve for an integrating factor. There are a group of equations in which this is true. So let's take a look at an example real quick. So let's say we're given 3xy plus y squared plus x squared plus xy dy dx equals 0. So we have m and n, and if we go dm dy, that's equal to dy of 3xy plus y squared, and that's equal to 3x plus 2y. And if we look at dn dx is equal to d dx of x squared plus xy, and that's equal to 2x plus y. And you can see that this is not exact. But let's see if we can find an integrating factor, mu of x, where that is true. So let's say that we have du on u is equal to dm dx minus dn. You got to be careful here. Dy minus dn dx divided by x, and so that is 3x plus 2y minus 2x minus y all over x squared minus or plus xy. So we have du on u is equal to x plus y over, and we factor an x out, and we have x plus y, and dx, I forgot the dx, and actually this, gotta be more careful. This is n dx, and that's dx dx, and this cancels, and we're left with 1 on x dx. And so we have ln u equals ln x, which is just basically u of x equals x. So now with that, let's see what that transforms the equation to. So if we multiply through by mu of x, we have 3x squared y plus xy squared plus x cubed plus x squared y dy dx equals 0. And if we take our dy d of m and d dx of n, we have 3x squared plus 2xy equals 3x squared plus 2xy. And now it's exact. And there's a solution. So we now have transformed the equation into an exact equation using an integrating factor of x. So we have, as we said, 3x squared y plus xy squared plus x cubed plus x squared y. I believe that's it. dy dx equals 0. And make sure I got that right. And so we have our function f. Our solution will be c, and that's equal to 3x squared y plus xy squared dx plus h of y and h prime of y. Gotta be careful. Y is equal to n, which is x cubed plus x squared y minus d dy of m, 3x squared y plus xy squared dx. And so if we carry out the integrations, we end up with x cubed y plus 1/2 x squared y equals, plus h of y is equal to constant. So we have to find h of y. Well, h of y, h prime of y is equal to x cubed plus x squared y minus, now we have d dy of the d dy of m, so that's 3x squared plus 2xy dx, and this is equal to x cubed plus x squared y minus x cubed plus, that's minus, actually, minus x squared y, and that's equal to 0. So h prime of y is equal to 0, and h of y is a constant. But adding a constant, let's say c prime, c plus c prime is another constant k, so our solution is x cubed y plus x squared on 2y equals k is the solution for the equation. And this is just an example. We'll be solving some more problems along this line in a little bit. I just want to go through homogeneous equations, which is basically how to transform an equation into a separable equation. We've already seen it to some extent, but this is a little bit more formalized. So let's say we have the circumstance dy dx is equal to f of xy. And let's say that the function f of xy can take the form of dy dx of f of y on x, or vice versa, or f of x on y. And there are circumstances where that can be done. For example, if we're given dy dx is equal to y squared plus 2xy on x squared, we have y squared on x squared plus 2xy on x squared, and that is equal to y on x squared plus 2y on x. So this is homogeneous. This is a condition of homogeneous equations. So let's say we have v is equal to y on x, which means that x, v equals y, and dy dx equals d dx of xv, and that is v plus d x dv dx, and that is, let's say, a function of v. So now if we move things around and we have v minus f of v equals minus x dv dx, and we do a little more algebra, and we have dv on f of v minus v. Let's see. Let's be careful. I'm not as careful as I should be. Let's say this is equal to dv on f of v minus v, okay? And this is dx on x. And then there we have our differential equation. So now we have a form here, dv on f of v minus v equals dx on x. Or actually we had it probably in a better way by saying dx on x equals dv, where we had it this way before, minus v. And so we'll leave it this way and just box our form in that way. So this is a way of making an equation separable and this is a homogeneous condition. And it gives us a way to solve problems. And in the next video, we're going to take a look at a number of examples. And from there, we're going to begin looking at applications. Radioactive decay is one. We've got mixing problems or first order equation, certain mechanics problems, variable mass problems, elementary mechanics with variable mass, rockets, and we're going to also look at things like pendulum motion. They give the Bachistochrome problem here. That's a fascinating problem. That's something that Newton solved, and it was a class or a new area of calculus called calculus of the variations. That was the first problem. And that brings us to the end of the chapter, and we will be moving into second order differential equations. Second order linear differential equations. So we're getting near there. And so we have only a few more, maybe 2 more videos before we move on to second order linear equations.